welcome to our meetup, and thank you for coming. I hear there's more pizza coming, right? Okay, all right. So before I start, I'm Debanjan, I run Aurora in Amazon. Before I start, let me do a show of hand. How many of you actually heard about Aurora? A lot of you. And how many of you have actually used Aurora? Very few. All right, so before we get into the technical topics, I have Lynn here, who is part of our business development team. And she has, Lynn, if you can show your hand, and she has, from what I hear, some Aurora credit card, which will give you $50 usage credit if you start using Aurora. So, feel free to collect it before you go. So, what I was going to do is to talk a little bit about what Aurora is and then get into a little bit more deep technical talk, right? The two things that Aurora is good for, and there are many other things, but two things we really do well is performance and availability. And I'm going to get into not only what, but also how we do that. And I don't know how much time I have, I'll go slow and maybe stop for questions, or maybe you will hold the questions for the end. I mean, whatever way it works, we'll have enough time to have a good discussion. And we have our speakers after me who will talk about, for example, the use cases that they're using Aurora for. So, what is Aurora? Probably easier. So, what is Aurora? Aurora is it's a MySQL compatible database. To be more specific, it's a MySQL 5.6 and InnoDB compatible database. Although it is surface area same as MySQL, we have actually changed a lot of things within that surface area, and I'm going to get into the details of how we have done that. Now, what we've tried to do, and we have been doing that really well so far, is that we want to have the performance and availability of commercial databases, but still at the price point and simplicity of open source databases. And that's kind of the high order bits in terms of what we are trying to achieve. And if you look at this is a very high level architecture of what it looks like. The Aurora works on a shared distributed scale out storage system. This is a storage system that we designed from scratch, and it spreads across 3 different availability zones. And there are hundreds of storage nodes within those availability zones for high availability and for performance that we use. And that shared storage structure then fits into the head nodes that we call the Aurora engines. We have a master, which can do both read and write, and you can add up to 15 read replicas, which can do read so that you can scale your read through. We do back up into S3, and I'm going to get into some of the details, but at a high level, I wanted to show what Aurora looks like. Now, why is this different from what you have seen in the past, both on-prem and cloud? We have enterprise class availability. So what we do is that we replicate our data 6 ways across 3 availability zones, right? So even if we have a complete outage of availability zone, which means a data center, you still have full read and write availability. We can fail over in less than 30 seconds. Crash recovery is near instantaneous, and I'll get into some of the details, but this is kind of the takeaway points so that you know what we are doing. In terms of performance and scale, on a large instance that we support, which is 8XL, that is the largest instance you have, you can do up to 500K reads per second and 800K writes per second, and which is 5x of what you can get on a similar instance with MySQL. We have up to, as I said, 15 read replicas. One of the things which is unique about Aurora compared to MySQL, for example, the read replicas have very low latency. It's less than 10 milliseconds in many cases, right? And I haven't seen that going up to more than 20, 25 milliseconds. Depends on the load. And if you compare that with MySQL running bin-log replication, which can very easily be a couple of seconds, sometimes minutes. Right? We have up to 64 terabyte of storage for each Aurora cluster, and it's an auto-scaling storage, so that when you start with 10 gigabyte of storage, and then as you add more and more data, it automatically adds storage to what you have, right? Which is quite useful, because if you use, databases today or databases in RDS, you have to start with certain storage volume, and when you need to add storage, you have to essentially go and figure that out and add your storage. You don't have to do that, it automatically adds storage to it. It's also offered as a fully managed service, which uses, if you're familiar with RDS, it makes use of the RDS control platform, control plane, so that, for example, things like provisioning, things like patching, things like backup, etc. are all automated. You don't have to worry about that. And customers are using Aurora. One of the things I'm very proud of is that it's the fastest growing service in the history of AWS, and it's growing really, really fast. Here are some of the customers who are using Aurora today. These are the customers I can talk about because they are public references. There are many others who I cannot talk about because they are not public references yet. I'll quickly go through some of the use cases that people are using Aurora for. Expedia, they use Aurora for their real-time analytics. They were using SQL Server. It was, of course, expensive, and as the data volume grows, it actually impacts performance. And they moved to Aurora. They also considered Cassandra, for example, but that didn't quite work out the way they wanted it to, and they are quite happy with Aurora. And some stats there, I'm not going to get into too much details. PG&E, all of you know PG&E in this part of the world. The reason they like Aurora is that they have web servers where during outage people come to find out about what's going on about their service. And when you have outage, or when they have outage, the amount of requests that they get can grow very, very rapidly, right? So what they really like about Aurora is that they can start with one instance and maybe a read replica. And when time comes and the load increases, they can very easily spin up read replicas which have very low latency. And that really helps them scale the database capacity that they want to have. Alfresco, this is one of the open source content management companies. They wanted to have 1 billion document repository in the cloud, and they were trying to use MySQL. Of course, it didn't scale that much, and they moved to Aurora. They have 1 billion document in their repository, and they can actually ingest 3 million documents per hour, and this is definitely something they are very excited about. Art Networks, this is an example where they have 10,000 neighborhood level sensors. They gather very fine-grained atmospheric information to provide very accurate weather forecasting on a localized basis. And the reason they like Aurora is that they have a lot of data that's coming in which they need to ingest and put in a database. So this is a very, very write-intensive application where they're streaming events from 10,000 sensors. They use Aurora to store that data, right? So it's kind of another example of how people are taking advantage of Aurora. So let me talk a little bit about, this is kind of changing gear a little bit. The two things I wanted to cover is performance and availability, right? And I not only what, but I also want to cover how we get performance and availability. This is some high-level numbers, as I said, that if we ran Aurora with Sysbench, this is a popular benchmark that we use, on an 8XL machine, which is 2 ports, 32 vCPUs, or 2 sockets, 32 cores, and 256 GB of memory. About 244 GB of that is used for databases, and rest is used for other things that we do in the system. And with Sysbench, we get a little bit above 100,000 writes per second, and close to about 600,000 reads or selects per second, right? Very impressive number. And by the way, I mean, this is very reproducible. if you want to try this out, we actually have a white paper on the website. You can go and try it out yourself. Right? What you need to do is essentially spin up an R38X large Aurora instance. And in order to get the best performance, we recommend that you use 4 load generators, each R38XL or some 8XL machines. And then you need to apply some network setting to your clients, enhanced networking. Without that, you actually have bottleneck on the client side. And if you follow the instructions in the white paper, you can very easily see that you can reproduce these numbers. Right? So this is not something just for marketing purposes. And but who cares about benchmark, right? Everybody is publishing some benchmark or the other. If you look at real world workload, request content with each other, the metadata rarely fits in the cache, data sometimes does not fit in the cache, you have to run high availability and disaster recovery, which people don't mention their benchmark numbers. So we actually tried to kind of simulate that with sysbench. Simulate in the sense that we didn't want to have any arbitrary workload. We wanted to have something that people can reproduce. So sysbench is a good workload generator for that. But we actually changed various different parameters to see how we can simulate some of the real world environment. So this is OLTP workload with 250 tables. And there is sufficient amount of contention built in the workload. And what we did actually increase the number of connections from 50 to 500 to 5,000, right? And compare Amazon Aurora with the RDS MySQL with 30,000 provision IOPS on 8XL machine. And if you look at the numbers, Aurora number actually with number of connections grows from 40,000 with 50 connections to 121,000, but then it goes down. And the reason for that is that MySQL has a lot of inefficiencies in terms of how it handles concurrency. And I'll get into some of that. One of them, for example, contention in the log manager. And in some cases, the thread pool becomes a problem. So we eliminated a lot of those issues, and that's why with increasing the number of connections, it scales very, very well. Then we changed the number of tables so that not everything fits in the cache. Right? We started with 10 tables, and we went to 100,000, 10,000, and we compared that with various different types of MySQL instances. We used MySQL with local SSDs so that there is no network storage effect. On MySQL, we used with RAM disk, and we also used EBS storage, right, which is network attached storage. And here, if you look at the numbers for Aurora, it kind of goes down a little bit when you reach 10,000 tables, but pretty much very steady, right? Increasing the number of tables doesn't really have any impact on performance of Aurora. If you look at MySQL on the other hand, and it's interesting actually, the storage is not really the issue, right? You look at SSD, you look at RAM disk, you look at network attached storage, which is the EBS storage, it's pretty much the same number, right? So something else is happening here, which is essentially contention within the MySQL engine code, and a lot of it has to do with the way various different data structure that handles concurrency in MySQL. Then we scale the data set size, right? You start with 1 GB, which fits in pretty much any cache. And then you went to 10 GB, 100 GB, which, in this particular case fits in the cache. But when you go to a terabyte size of database, of course, that does not fit in the cache in this particular example. And if you look at the numbers here again, running sysbench write only, in case of Aurora, up to 100 GB, when you fit this in the cache, the performance is still roughly about the same. And of course, when you go to 1 terabyte, which does not fit in the cache anymore, performance goes down, which is what we expect. But interestingly, if you look for RDS MySQL, performance starts going down when the size of the database is 10 GB. It goes down further, 100 GB, and then 1 terabyte, it of course is lower than that. So the performance is not just impacted by not being able to fit data in the cache, it's also impacted by something else, which again, the way the code path, the right data path works in MySQL. And some of these numbers, the improvements is crazy number, 67x, which is, we don't even say that in our marketing literature because it's a crazy number. We said that, is this right? And we tried a different benchmark, Cloud Harmony TPCC, which is very close to the TPCC benchmark that you get from the TPC organization. Unfortunately, you cannot run that, so you use something different because TPCC or TPC does not recognize benchmark on the cloud. And here, if you look at the number, it's even higher, it's 136x. So one thing we do pretty well, as you can see from some of the numbers, we handle the scale very well, whether it is the number of connections, whether it is the number of tables, whether it is the size of the data set. In fact, higher the scale, more conspicuous the performance differential is. Okay? We did the same thing with read replicas, right? I mean, this is an example of where you are adding high availability in the mix. And if you look at the read replicas, and we increase the number of updates per second from 1,000 to 10,000, and for Amazon Aurora, the read replica lag goes from 2.6 millisecond to 5.3 millisecond. And in case of MySQL, it can go as high as to 300 seconds. Right? Now, which is 500x better in terms of the lag that we see. So how do we do this, right? That's probably more interesting than just the numbers. And there are many things that we have done. Some of this is just pure engineering. We looked at the code base, we did some optimization. But there are two fundamental things which is different in Aurora. One is that we do a lot fewer I/O than what you do in a traditional database, MySQL in particular, in this particular example. And we do a lot of processing asynchronously. So we are not really stuck on anything. We use a lot of lock-free data structure, and we do a lot of asynchronous processing so that we make use of our cores much better than you see in MySQL, for example. And database is all about I/O, and if you can reduce the number of I/Os, you get huge amount of benefit. So that brings us into the architecture a little bit. So what is the specific difference between the Aurora architecture and the traditional database architecture? If you look at database architecture in general, right, it hasn't really changed in the last 30 years. You have a monolithic stack where you have the SQL processing, transaction processing, logging, and storage as a part of that stack. And what we are trying to do is to kind of re-architect that for a cloud environment where you took that monolithic stack and took two layers of that, logging and storage, and spread that out into a scale-out, multi-tenant shared architecture, right? So in this particular case, and we plan to do, by the way, the same thing for other layers of the stack. We want to have a distributed caching layer. We want to have a microservice which will do, for example, query optimization, right? But what we have done so far, combining the logging and storage and creating a storage architecture which is optimized for databases and optimized for cloud. Now, what do I mean by that? This is kind of a high-level architecture of the Aurora cluster. And if you look at the storage architecture, it's a shared multi-tenant storage where each copy of data is actually written to 6 different storage nodes across 3 different availability zones. Right? So you're writing essentially 2 copies of data into 2 storage nodes in an availability zone. And we do that primarily for availability. But there is another aspect here which is very, very important from the performance point of view. The storage that we have is not a regular storage. It's not iSCSI or NFS or typical storage architecture like that. It's a log structure storage which does a redo log API. So what we do is from our engine, we are not sending the 16K buffer pages. We are actually sending just the redo log record, which then we apply in the storage node to the data pages and create the data pages in the storage node itself, right? Just to complete the picture, the Aurora read replicas are kind of connected to the storage node, the way it's shown here. Now, if you compare this with what we do, for example, in RDS MySQL or any other database for that matter, is that these are some of the write data path traffic flow inside the database, right? In this particular case, if you have RDS MySQL, from the primary instance you are writing to the EBS volume. EBS does an asynchronous mirroring, so it's getting copied into a secondary volume. Then you are doing a bin log replication, which is going to a standby instance, right? Or not a bin log replication, we do a different type of replication in this particular case. And it goes to the standby instance. From there you are writing to the local volume of the standby instance, and then you are writing to the parallel volume that EBS maintains as a mirror. Right? So there is a lot of data traffic that's going in there. If you compare that, if you look at the number of I/O that we do in order to have certain number of transactions, so what we did actually, we ran sysbench write-only workload for 30 minutes with a 10 GB data set, and we got 780K transactions in that 30 minutes. And there was a total of 7.3 million I/O transactions, an average of 7.4 I/O per transactions. Right? So that is what you see when you run in a traditional database environment. If you look at Aurora, what we're really doing here, that we are collecting the redo log records. We are kind of putting them in packets by doing some compaction, right, from batching. And then we are sending that over to the storage node. And remember, in this particular case, we are actually sending it to 6 different storage nodes, right? So it's not, we are actually doing some amplification that way because we are writing it 6 times for reasons of availability. But amount of traffic is so much lower that even with 6 copies, the total number of I/Os is 1/8, almost 1/8 of what you see in case of MySQL writing to EBS, right? That's one of the primary reasons, by the way, that even when we are writing 6 copies of the data, we are actually getting much better performance. Important thing to remember. These are some of the details in terms of what happens in the storage node. I'm not going to get into too much into this, but this is where probably the most of the innovation of Aurora is embedded in. We also do a couple of other things. We do asynchronous group commits, and we do that in batches. I'm not going to get into too much details here. This is very different from what you see in traditional MySQL, for example. One of the reasons asynchronous processing helps us. Adaptive thread pool is another area where we have a lot of innovation in, and we actually dynamically spawn threads based on the amount of work that we have. Very different from what MySQL CE does, and even different from what MySQL Enterprise Edition does. Another interesting piece in terms of I/O traffic is how we handle read replicas. If you look at MySQL, the read replica actually is using bin log replication, right? Which is essentially a logical replication. You're shipping your SQL statement from primary to your standby or read replica. Then you're applying those SQL statement. So if you have some amount of write load on your master, you are essentially doing the same amount of write load, applying the same amount of write load on your read replica, because we have to apply the bin log to the read replica, right? In case of Aurora, what we do, we are not doing bin log replication. All we are doing is sending the redo records to the read replica. And the read replica is connected to the same shared storage volume, so you don't really need to update it. Only thing you need to do is that if there is a buffer page in the memory of the read replica, where the redo log should be applied, we apply the redo log to that buffer page so that they are in sync. right? So it's a much lighter weight protocol that we have compared to bin log replication that traditional MySQL read replicas do. There are many other improvements that we are doing. I'm not going to get into the details of that, and we kind of do code releases pretty much every other week, and you can hope to see a lot of these features coming online soon. Now, right, so this is very important, right? I mean, you can generate whatever performance you want to generate, but if your database is not up, it doesn't really matter. So, again, I think a lot of innovation has gone into the way we have architected storage, right? And what we do really is that we have essentially 6 copies of every data spread across 3 different availability zones on 6 storage nodes. Now, we have many more than 6 storage nodes. In fact, if you look at the Aurora storage cluster, we typically have about 1,000 storage nodes. Within each of the storage nodes, we have 8 SSDs. So you're talking about 8,000 SSDs where we spread our data across, right? So we take 10 gigabyte segments and then spread that across 6 storage nodes. The next 10 gigabyte segment gets spread across another set of 6 storage nodes. So as you have a larger and larger volume, you're using more and more storage nodes, both in terms of scaling your capacity as well as scaling your performance. Right? So if you are scaling or striping your data across hundreds of storage nodes, you can aggregate all the capacity and all the performance you can get from so many storage nodes that you have, and that's what actually drives performance as well as availability. Now, in terms of write, we do a 4 out of 6 quota. So whenever you write something, you send it to 6 different storage nodes. As soon as you get response back from 4 of them, the fastest 4 of them, right, we commit that particular data item, or we assume that it's stable now. Now it actually helps in 2 different ways. One is that you need only 4 out of 6 storage nodes. So if your entire availability zone, which is a data center, goes down, you still have full write availability. If you have 2 of the storage nodes going down, you have full availability, right? And when one of those nodes or one of the AZs are down, we have new nodes coming up, and there is peer-to-peer replication going between the storage node, so that there is a background repair action that is happening, right? So I'm not, there are a lot more things, of course, happen, in the code. Not getting into too much details here. A couple of other interesting things about Aurora. Our crash recovery is almost instantaneous. So what does that really mean? If you compare this with MySQL, for example, does checkpointing every 5 minutes. And if there is a crash after that, you have to apply the logs since the checkpoint to your storage before you can get it up and running, right? So in the worst case, you have logs worth 5 minutes of writes that you need to apply, and that log application is single-threaded, so sometimes it takes more than 5 minutes. Actually, it can take half an hour in many cases, right? What we do in Aurora is that we are not really doing that checkpointing thing. Right? All we are doing, we are sending the redo log records to the storage nodes, and when you come back after crash, we apply those redo log records asynchronously and in parallel to the pages in the storage node, so that it takes really fraction of a second to come back after a crash, which is very, very important and improves our failover time. Another concept we introduced is survivable caches. So we have taken out the caching process out of the MySQL D and made it a separate process. So as a result of this, when your MySQL D crashes, or you have to restart it because, for example, you have a deadlock, your cache is still warm. When you come back up, you don't have to reload your whole cache. So performance remains much better after a crash recovery than you can do when you have to restart your cache and reload all the data in the cache. So if you add all of this up, where do you end up, right? So it's much faster, more predictable failover. How do you get there? This is comparing MySQL with Aurora, and I'll talk a little bit about the MariaDB driver. So when MySQL crashes, we do failure detection, which takes some amount of time. Then the recovery starts, and in case of recovery, in case of MySQL, recovery can take an non-deterministic amount of time. It depends on where the checkpointing was done, how much of log you need to apply, and many other things like that. And in parallel, there is a DNS propagation going on, which helps you switch the endpoint from the master that died to the new master who is now picking up. And in case of Aurora, the failure detection time is roughly the same. It's about 15 to 20 seconds. But the recovery time is much, much faster and deterministic. It takes anywhere between 3 to 20 seconds. And while the DNS propagation is going on in parallel. And if you use DNS to do the failover, that is, it allows you to figure out who the new master is, it takes roughly about 60 seconds. Now we have a driver which is an extension of MariaDB driver for MySQL. In fact, MariaDB added it in their original driver. Is that we don't really need to wait for DNS propagation to happen. It reads a system table within MySQL and figures out who the new master is without having to wait for the DNS propagation. And if you use that driver, the failover is roughly about 30 seconds. Okay? Significant improvement. And we have a bunch of SQL commands, by the way, which you can use to try this failover and try it out for yourself, simulating different types of failures and see how much time it takes to do the failover. Okay. So I'm going to stop here because I think it has been probably a little bit of a dense presentation. And I would like to open it up for questions. Whatever questions you have, I'll be happy to answer. All right. So, go ahead. Is there another mic we can?
What you're doing here is really very impressive. Could you give us, especially the entrepreneurs amongst us, an idea of what kind of cost we're looking at to deploy Aurora?
So the cost in terms of compared to MySQL or compared to Oracle?
No, just cost, period. In dollars and cents. In other words, if I wanted to use Aurora.
Right. So the smallest instance that we have is, I believe, 29 cents an hour. Okay, and then there is a storage cost that you have to pay, which is 10 cents a gigabyte per month, and then there is some I/O cost. But the right way of comparing this probably with what you have to pay when you use some other database, right? So we have done some analysis. Compared to commercial databases, it's about 1/10 of the cost. And compared to even MySQL, the cost is lower, although the instance cost is slightly higher than MySQL. But you save a lot of money in storage, and because the performance is so much better, you can probably use a smaller instance and get away with that.
So if my understanding is correct, what it means is that if I want to use Aurora, I'm not just getting the hosting, of course, but I'm getting the database and at the same price to all intents and purposes.
Good.
It can be programmed and then scaled just about infinitely.
It can be, I wouldn't say infinitely, but to a quite large instance, yes.
So you talked a lot about the innovation in the storage there. How much of that is generalizable, and do you guys have any plans on kind of making it available as a first-class AWS service?
Well, it is potentially generalizable. We do actually have an internal iSCSI driver which we have tested lightly. We currently don't have any plan to make it available as a general purpose storage layer because there is a lot of optimization we have done in the redo log processing, which kind of serves very well as a database engine, database storage engine, right? And maybe in future someday we'll consider that, but we currently don't have a plan to make it available as an independent service. Any other questions? Go ahead.
So we gain a lot of things as compared to MySQL RDS. What do we lose?
Well, compared to MySQL RDS, you don't really lose anything. In fact, when I recommend customers, we say that if Aurora is available in a region where you want to use a MySQL compatible database, Aurora is better choice pretty much in all respects. We don't have Aurora available in all regions yet because it requires 3 availability zones and not all regions have 3 availability zones. Right, so that is a restriction we have. We also have Aurora available only for R3 large and larger instances. Right, so if you want to use smaller instances, then MySQL is still a better choice.
In terms of architecture, because you have some asynchronous stuff here
right.
as compared to MySQL RDS, does that bring in any uncertainty?
No. The asynchronous stuff is all internal. It is not doing, for example, asynchronous replication or anything. It's the way we handle the handover between various different threads, right? And instead of blocking on a mutex, we use lock-free data structure so that if somebody needs to wait for something, it actually hands it over to somebody else, and when the response from the storage system comes back, we call a handler to process that response back rather than waiting for it. Right? That's the way we use asynchronous.
And do the limitations of gap theorem ever kick in at any point?
No. This has nothing to do with gap. I mean, this is all standard relational database with passive properties. Yeah, go ahead.
I understand it works like a relational database with passive properties, but does it relate at all, no pun intended, to a relational database, or is it you accept commands that we all know to talk to a relational database, and it's completely like Amazon wizardry on the back end?
It is a pure relational database. It's not trying to have a surface area API like a relational database. It's a pure relational database.
But I mean, are there tons of tables sitting there replicated across the 3 zones? Like when you write the 6 places across 3 zones, are you talking about actual physical database tables?
That is really at the storage layer, right? So it's still one table that we're writing, but at the storage layer we are keeping 6 copies of every piece of that data.
It's beautiful. I mean, but it's not like writing the 6 MySQL database, like equivalent storage systems, right? So.
No, it is not equivalent to 6 MySQL databases, right? It's a single MySQL database, but underneath the InnoDB storage engine, you have a different type of implementation of that, right? So at the storage layer, think of this in some sense like S3, right? You keep 3 copies of data. So you keep 6 copies of data, but we are doing 4 out of 6 quorum to make sure they're all in sync.
So you acknowledge only when you have at least 4 of them in sync?
Correct. Thank you.
What situations are you working on?
Well, without kind of spilling the beans, there are a few things that we really want to do. I mean, it is still a single writer system, right? So we want to do a multi-writer system. That's one of the things that we are working on. One thing that we have done very successfully is to improve throughput compared to MySQL and compared to other relational databases. But we haven't done a whole lot of work in improving the latency of a single query, right? So for example, we haven't done a lot of query optimization. So that's one area that we are working on, right? So there are a few other things that we do on the back end that we are working on, which you probably don't see, but improves. For example, the way we want to do a point-in-time recovery. We have a point-in-time recovery, but it's not instant. So we want to do an instant point-in-time recovery.
You talked about 64 terabytes limit. Can you talk a little bit more about, like, is it data-wise or just like whole database? And how do you mitigate like bigger sizes than 64 terabytes? Something else.
Well, we are very happy to have 64 terabytes. So,
with the kind of growth we are seeing in big data.
Sorry, say that again?
With the kind of growth we are seeing in big data.
Yeah, so I think, can you repeat the question? Sorry,
I heard like 64 terabyte,
right.
Until 64 terabyte there was a kind of limit. Can you talk about like, if database size increases above that, how do you mitigate?
So we cannot actually mitigate that, right? I mean, we essentially give a warning saying that you are hitting that limit, and beyond that limit you won't be able to continue with your writes. Right? So that's the way you stop it. You cannot really go beyond 64 terabyte right now. There is, by the way, no architectural limitation in terms of 64 terabyte. We can easily go beyond 64 terabyte. But you have to stop somewhere, otherwise it kind of becomes unmanageable in terms of how we do capacity management. But we plan to increase that over time, so I don't think that will be a major issue. And for most OLTP databases, 64 terabytes is actually a lot, right? And we have customers who are currently using NoSQL databases, for example. They want to move over to Aurora because 64 terabyte is big enough for them. And they find Aurora to be more attractive because it's easier to program. It's simple SQL, right? And it also has ACID properties and other things. Okay, go ahead.
Hi, a couple questions. First one is, after seeing the storage layout there and the intricacies therein, I want to ask you, how is the KMS integration going? And the second question is, if we're making changes to the schema, adding users, giving grants, creating tables, dropping tables, are you capturing an audit log for that? Do you have an audit table, or is that something that you intend to send to CloudTrail at some point?
Yes, good question. I think in terms of KMS integration, it's imminent. If I delayed my trip by a couple of weeks, I probably can announce it here. Okay, so that's coming soon. In terms of audit logging and stuff like that, we do a lot of logging, but we don't have, quote unquote, the audit plugin here. Right? That is something we are planning to add, hopefully sometime early next year. Right? In terms of adding tables, dropping tables, and things like that, that's another area of innovation that we are working on. Currently it is fully compatible with what MySQL does, but we want to do online DDL in a much better way than supported MySQL. So that's another area of active work going on.
Do you only support InnoDB at this time?
Yes. And we actually plan to stay with InnoDB because we don't want to kind of support 1,500 different storage engines. I think that innovation really is a layer below InnoDB, not layers above it, right? So we plan to stay with InnoDB.
Do you support partitioning?
Yes, it's whatever MySQL 5.6 does, I support the same thing. Right, it's fully MySQL 5.6 and InnoDB compatible, and we have been running this for, including the beta, probably for about 1 year. I haven't had any complaint about incompatibility with MySQL. Good question. So we do support cross-region replication, which is through binlog replication, not the Aurora replication that I talked about. We do have plans to support it at the storage layer, which will be more performing than doing cross-region using binlog replication. I can make this available. This is actually, a lot of these slides are presented in reInvent, and you can go to YouTube or SlideShare and probably find most of the slides. I'm going to make these slides available as a PDF so that it can be distributed to people attending. Okay? Ready? All right. Now my friend Shinde is going to talk about how they are using Aurora in GoGuardian. Thank you.
Thanks, guys. Give me a second to get set up here. While we're doing this, how many of you guys use MySQL in prod? And of you guys, how many of you are considering moving to Aurora? Okay, so my goal is to really speak to you guys. As much as the Amazon folks tout the awesomeness of Aurora, they're kind of the creators of it. So, but we're running Aurora in prod, and so I have some real cool real use cases. Like we run this every day. So hoping to help you. So to give you guys a little bit more context, I'm the co-founder CTO of this company called GoGuardian. We're in El Segundo, and my 10-year-old cousin uses a Chromebook every day of his entire life, and he does this in school. He doesn't have any paper on him, and all of his exams and all the essays that he writes and all the worksheets that he does are through a computer. And when we were in school, we didn't have that, and we're seeing this as a major trend in education. Children are learning with laptops every day, and GoGuardian is a company that really facilitates that and makes that actually possible by not only collecting data about what students are actually doing, but protecting them from the bad parts of the internet. So that's what we do. The general theme of this talk is insane growth with an insane amount of resource constraints from an engineering perspective. So this is January 2014, if you guys can see, and the right is roughly present day. As you can see, we kind of grow, it looks linear here, but the points where it's flat is really just summer. So it's very, very, very kind of scary growth. And I think we hit the 1 million student mark with 3 engineers. So lots of scalability problems. From an engineering perspective, what we actually do is we collect data about what students are actually doing on their computers. So when they watch a YouTube video, we collect metadata about like what the video is, what the title is, what the YouTube video ID is, and in aggregate we pull all of these events in and show this information back to teachers and school administrators with the goal of improving learning. So as we hit the million student mark, we had engineered a solution that worked great for 10,000 students or 100,000 students, but we were having lots of difficulties at the million student mark. And the Amazon Aurora announcement happened right around here, and we were absolutely thrilled because it was like a free 5x gain in scalability. And we couldn't really re-architect our data storage layer or our data pipeline with 3 engineers because we were still building features as a startup. So we were absolutely thrilled, and let me tell you how it ended up working out. And before I continue, if you guys have any questions, please like stop me in the middle. I'd love to make this like a back and forth. So yeah.
What were you using before?
MySQL. Yeah. So we had built everything. It was a PHP MySQL monolithic app. We were moving really, really fast and shipping features. And the whole MySQL compatibility thing was kind of a very, very holy grail. So, solid question. So I think the first thing that you guys are wondering is the performance boost is real. They're not just making up benchmark figures. And let me show you why. So this is a graph that we have in one of our inserting applications, like database insert applications. The red line is actually the 95th percentile insert latency, and it's amortized because we're doing bulk inserts. The blue line down here, which is essentially the x-axis, is the median latency. So you can see we deployed Aurora right here. And you can see the 95th percentile just drop, and it's like 1.88 milliseconds per record. And yeah, obviously when you're measuring medians, like you don't really see an appreciable difference. I think the Aurora team talks a lot about throughput, but we really noticed it on like the extreme ends of inserts and also reads. Here's another application we have. This is just a sample API endpoint. And we have, again, the 95th percentile in red. You can see the median jumping up a little bit to maybe 1 or 2 milliseconds. But it just drops. It's like the deployed again. So absolutely phenomenal for us from that perspective. Another thing is, you guys should use read replicas. I think the Pinterest engineering team actually published a blog post earlier this year about how they managed to scale to, I don't know how many hundreds of millions of users that they have. And they managed to do it with MySQL sharding. And it's a very, very, very good blog post. You should definitely check it out if you use MySQL or want to shard MySQL. But one of the points that they bring up is that with regular MySQL, slave or read replica lag is very much a problem. And it results in issues like this. So sorry for the crude drawing, but here you have a vertical line representing time. So that's the beginning of time, and this is the end of time. And if you write foo equals 1 to the master, eventually it will propagate to the read replica. But if you perform a read of foo, anytime between when you make the write and when the propagation happens, you get an inconsistent read. And this is a huge class of errors. And we actually noticed this in prod when we were actually reading off the MySQL replica. And with Aurora, like, we're actually seeing tens of milliseconds or less than 10 milliseconds. I took the screenshot earlier this morning, like 2, 3, 4 milliseconds of replication delay. So for transactional writes, for example, if you're writing a bank balance account, maybe this is a problem. But for non-transactional writes, for example, if you're logging YouTube metadata, then this is less of a problem. Here's a spike that we have of, this is vanilla MySQL, and it's a replica lag that we have on RDS proper. So MySQL on RDS, and the y-axis here is actually in seconds. So it spikes up to well over 700, or so almost like 12 minutes of replica lag, which is absolutely absurd from like an application perspective. So we actually saw this as a real graph in production, and our customers saw this as well. Here's a snapshot of the maximum replica lag that we're seeing for all 4 of these read replicas here. And now the y-axis is not seconds, it's milliseconds. And it doesn't even go above 20 milliseconds over the course of, I think this is 3 days over here. So we're actually, this is real graphs and real prod. No benchmarks. So I'd like to rebut the Pinterest engineering team. If you're using Aurora, you should think about using read replicas, because the replica lag is really a game changer compared to regular MySQL. How many of you understand what an IOP is? How many of you understand what an IOP is in the perspective of MySQL select statements when you're an application developer? I think it's a very, very hard problem. When you go to provision a regular vanilla MySQL RDS instance, you get a little screen like this, where you have to allocate some amount of storage, and then you got to provision some amount of IOPS, and you're an application developer, you're writing these select and insert statements, and you don't really understand how that translates to IOPS. And I don't think anybody actually does. All you know is how many IOPS you're consuming for a real application, and then you just ratchet the number up 1,000, and yeah, you get a little bit better performance, but it's such an opaque metric. I'm really, really happy that the Aurora team decided to forego it, and instead, it's just 2 cents per million requests. And here's some actual real cost numbers for Oregon. The storage rate, as well as the I/O rate, as well as like the instance rate that you pay. So yeah, that was a huge win. Another huge win for us was really fast failovers and restarts. This isn't really like I guess you guys do talk about availability, but we've seen failovers happen, and failovers do happen. It's silly to architect a system without the expectation of something failing over. And here's a real application graph. Here you have 7 and 12 and 30 seconds, and then I think this is about where the failure happens. The y-axis here is latency in milliseconds, so you see our API endpoint really, really suffering because of it. but literally 1 minute later, it is fully subsided, and I have a feeling that this is so wide because of actual DNS propagation, and not necessarily because like Aurora is failing over. So definitely going to check out that MariaDB driver because I think that'll like lessen this gap. But yes, failovers do happen, and in the MySQL world, whenever we failed over, like we would be minutes, sometimes like tens of minutes before things actually came back online. And it's pretty awesome that you can fail over, restart within like less than a minute. Final point. So this is less related to Aurora, but we really learned this the hard way. And I think if you take one thing away from this talk is don't write to your MySQL or whatever database directly. You should buffer your writes with Kinesis or Kafka. This was our original like monolithic PHP MySQL application. And this is how a lot of startups get off the ground, and this is where we really proved our business value. But it kind of started to break in this situation. So over here, you have y-axis as incoming write throughput in the form of HTTP requests. So here we're ingesting data, so as students use their Chromebooks, we're collecting data about what websites they're visiting, etc. We don't really have any control over what's happening here, so it's just this big blue roller coaster. As time goes on, you have a real practical maximum of what your database write throughput is. And it's a finite number. And a lot of startups don't really hit it, or companies in general don't really hit it, but it's really, really important that you know what that ceiling is, because when it hits, how is your application going to perform? Like if you are forced to ingest all these writes, like what does your application do? And for us in this architecture, the answer was we just dropped the writes on the floor, and that is obviously not okay. So what we did is we push writes into Kinesis first. And this provides a bunch of widgets I'll get to in a second, but for those of you guys who don't know, Kinesis and Apache Kafka are essentially distributed message queues or write-ahead logs almost, where you can write stuff into them in a very, very high throughput way, and you can have multiple readers that read off these streams and do stuff with it. So in our case, we're pulling hundreds or thousands of messages off this Kinesis queue and bulk inserting them into MySQL. Or now I guess it's Aurora. So the Kinesis and Kafka throughput is obviously naturally much, much higher than MySQL as well as Aurora because it's not doing any application logic with it, it's just buffering the logs. It's also very easy to add more data stores. So this was a very unintended consequence of our architecture design. We didn't really expect the use case of adding more data stores. Instead, we were very, very reliant on MySQL and Aurora, but we needed this buffer in the form of Kinesis and Kafka to deal with this dotted blue dot problem. And as a result, as a side effect of this architecture, we are able to just add more readers to our Kinesis stream and insert into other data stores. So now we're branching off into using S3 as like raw data storage, as well as other data stores like Druid. And it's all possible because we buffered our writes. And that's really all I have to say. So my name is Advait. If you enjoyed this stuff, come find me afterwards. I have a whole bunch of GoGuardian stuff here. So if all you want is GoGuardian stuff, you can come say hi and I'll give you some. But yeah, thanks for listening. Appreciate it. Up next is Kevin from the CorpInfo team. He's going to be talking about how to migrate from MySQL to Aurora. Everyone, welcome Kevin.
So hopefully you've taken away some really good information from both Debanjan and Advait. I think Aurora is pretty exciting. I think it changes a lot of games for a lot of people. Very interesting that people are going back from NoSQL back to a relational database. And you've heard a lot about how Aurora is MySQL compatible. And I guess the point of what I'm going to try and show you now is just to the extent of how compatible it is. I had more of a demo arranged, and I started puking up some ODBC errors, so we won't be showing you those. But I can show you just how simple it is to go from a MySQL database off to a Aurora database. Alright, so what we have here is just regular accounts. This is a very simple PHP app. It's a site that's run just for a hobby of mine. Because I like airplanes, and it also gives me a really good test bed for various things I'm trying in Amazon. What we're going to do, this is currently backed by a RDS MySQL database. The idea is to take that database, dump it, ingest it into Aurora, and flip the connection strings in WordPress, and it should be as simple as that. The site should stay up and continue to run. There's a couple different ways you can do this, though, and I wanted to show you one slide in particular, this one here. As Debanjan mentioned, because this is a MySQL 5.6 database, essentially compatible with MySQL 5.6 and NODB, there's not a lot you have to do. If you want to be lazy, you don't even have to do all of these steps. The right way, though, is make sure that you're running MySQL 5.6. Make sure you convert any ISAM tables to NODB. If you're running MySQL in multi-AZ mode, you should have already done this. It's something that Amazon talks about for MySQL RDS anyway. Before you do any changes, make sure you've got backups. And one of the ways of moving from MySQL to Aurora is to actually go and migrate from snapshot. And so that is the first way I'm going to show you how we can do migrate. There is something to know about this, and that is you cannot do this off a manual snapshot. So if we have a look here, you'll see I have a couple databases. I have a MySQL multi-AZ RDS database, and then I have Aurora multi-AZ, and you can see one of them is a reader and one of them is a writer. And if I wanted to convert this database, for example, into Aurora, we can select that MySQL database. We essentially say migrate latest snapshot, and you don't get an option to say this manual snapshot. It's always an automated snapshot. So you basically say migrate this one, you select your instance size. It's going to suggest a name for you, you can change that. You pick which VPC you're going to run it in. Pretty much things you've seen and done for RDS already. There's nothing different here. What is absent here and was mentioned already is you're no longer provisioning storage. So they just don't ask. They don't ask how much you want of the storage, and they don't ask how much I/O you're looking for. You hit migrate, and within, depending on database size, this is going to take a little bit of time. So while that's happening, I will show you a more manual way of doing this. If you've worked with MySQL, you've seen these. You've seen a lot of this already. You can see we're migrating this one here. Let me grab one of these machines, IP addresses. One other change just to allow some security, open up some security. So this is just vanilla Amazon Linux. And the first thing we want to do is just a MySQL dump of the database. So what we're doing here is a very standard MySQL dump. This is stuff you've seen. At this point, we aren't even talking to Aurora. It's just plain old simple MySQL. And so we have a dump file. This is, you've all seen this. Here's where things get a little different, but very much the same. We're going to do a MySQL ingest of this, but into Aurora. And there's no trickery, there's no change in drivers, there's no change in software. We're using standard MySQL software to import this into Aurora now. This is, and we're going to send this into the writer, and it will then replicate to the replicate to the reader. So again, just standard MySQL stuff that you've seen. Double check if that's the correct user on this thing. AWS start. So this is a pretty small database. It's only about 38 megs, 40 megs. So this will take a couple seconds, and then it's ingested. So just so you can also see again what it looks like if you're using Navicat, you can connect with or MySQL Workbench for that matter. You just connect with the regular MySQL drivers, and you can see there. This database is the one we've just imported. Something interesting that I like to show is, and actually I'll show it to you over here. Let's first log in. I mentioned if you're lazy and you don't want to do all the things you should do, such as updating from MyISAM to InnoDB, Aurora will do that for you. So. I have a small piece of SQL. What I wanted to show you over here. So you can see the source database. I have a couple of MyISAM tables, the majority of them are InnoDB. If I then go to the Aurora database that we've just imported to, and all we did was a simple MySQL command to import Aurora actually will convert those for us. So if I run the same query now in here, what we'll see is that they've all been converted to InnoDB for you. So again, probably not the best way to go around doing a production migration. This is a simple little WordPress site with very little going on inside of it, so it makes it easy. I wouldn't recommend it. I would recommend do your snapshots and your backups. Make sure you're at the correct engine level. Make sure that you convert the tables in a sort of sane and controlled manner, and then do the MySQL import. I mentioned there was another tool that I'd hoped to demo. It's the RDS migration tool. I didn't get it to work. I have no doubt it does work, but I got a lot of ODBC errors. But one of the things that is a little bit tough about it is actually finding it. And so I wanted to show you how you can go about finding it. And if you want to experiment with it, play with it. It's probably a tool that's more interesting to you if you're going from an Oracle database or a SQL database to Aurora than if you're just going from MySQL to Aurora. So a little non-intuitive on how you're going to find this tool. You're going to go to AMIs, and you're going to go look for private AMIs. And if you then search for migration, you'll find that you can launch that tool. And there's some documentation on how you actually use it, and I can share that in the notes for the meetup later this evening. So at this point, what we've done is we dumped the database. We've also ingested it back into Aurora. So the last thing I have to do here is copy or update the WordPress configs to go and point at Aurora. So I've already pre-prepped this WordPress config file, database name, username, password, and you can see I'm pointing at the Aurora cluster. And so this connection string here is something interesting to note. If we take a look at Aurora, it essentially lists the reader and writer as two different databases, but they're related to each other. So you can see here, I have AWS demo, and I have one with a slightly different database instance name. One's the reader, one's the writer. And if you look here on the writer, we have with cluster in the name. And if you look at the reader, you will see that they've just got, instead of cluster, they're telling you which zone this reader is actually residing in. So for all of your transactional work, you're going to always point at the one at your cluster, that should be your writer. And then, if you have very high read loads, you're going to point your application at those specifically. So next thing to do here is this what we've done there is nothing more than just change the configuration for WordPress, and because that dump it was from just a few moments ago, the site's up. It continues to work the way the site should work, and I haven't re-engineered my application at all to make Aurora work for me. So it's a simplistic demo. It's not meant to show you all the worst about database migrations, but it can be that simple, and a lot of customers are seeing that it is that simple. So that's what I have prepared for you in terms of demos, and the guides are responding, so it all worked kind of the way we expected. Any questions?
You track aircraft by the manufacturer? You track aircraft by the manufacturer?
Yeah, I do. I don't have a very large database, but a good portion of this is just me at LAX or Long Beach or any other taking photos. I've got a bunch of people around the world who send some as well. But yeah, if you search for if you search for things correctly spelt, you will find a whole bunch. And the performance here is more a function of the web instances are really tiny things. Again, this is sort of just my personal project, and it's really about a test bed for me and for the things I do on Amazon. But if you have a look here and search, let's say, Boeing, Donald Douglas, so there's only one Donald Douglas plane apparently. Embraer, maybe a couple more. But yeah, this is just, again, really the point of this is to show you that when they say it's MySQL compatible, it really is, and it's very simple. And your migration path can be very simple, depends. If you have a lot of complicated triggers and a lot of complicated store procedures, you're probably not going to do a simple dump and ingest and make things work on the first attempt. You know, if you're going to go from engines like SQL or Oracle, that is a whole lot of different ballgame. You're going to change not only your store procedures, not only your triggers, but your drivers are going to change, your code is going to change. It's going to be a lot more painful, but on the far side of that change, you will see very significant gains.
Hey, for like PBO, is there like another level of abstraction, or do you actually have to rewrite MySQL code that works with the driver?
So, if you're working with MySQL, the amount of rewriting you're going to do is going to be fairly limited. If you're moving from SQL Server or Oracle, you're going to do a lot of rewriting. Some of that also depends on how much of your logic is sitting in the database. I'm not a big fan of store procedures, but if your application logic is in there, you will be doing a bunch of rewriting. For the same matter, if all of your application logic is in code, acquiring some special reserved keywords, your SQL statements should mostly work. So, any other questions? Well, if there's no other questions, I want to thank you all for coming out, taking the time coming out. I know you've all had long days and this is your time. I want to thank the Amazon team for coming out and presenting. I heard from GoGuardian again. I think it's important, it's really helpful and useful to have Amazon come out and talk about the product because they are the authority. But I also feel that real-world customers sharing their experiences in many ways is more meaningful because we're no longer talking about architecture, we're talking about this is what they were able to do and able to achieve. And I think that also just has sort of lends an air of credibility to the product. The company I work for, CorpInfo, sponsored dinner this evening. We ran out, so we bought more for you.
Yeah!
Hopefully we'll be meeting. I've done a pretty poor job recently of keeping the meetups going. Looking for ideas, so if you have topics you want to talk about, let me know. Put it in the meetup board and let me know what you want to hear about. The Amazon guys are really good about getting speakers if we give them enough notice, and I think this is really just, this is for you guys to come out, learn, do stuff, and so the more that you tell us you want to learn and want to see, we'll bring that back for you.